The absorption of electromagnetic radiation by water depends on the state of the water. The absorption in the gas phase occurs in three regions of the spectrum. Rotational transitions are responsible for absorption in the microwave and far infrared, vibrational transitions in the mid-infrared and near-infrared. Vibrational bands have rotational fine structure. Electronic transitions occur in the vacuum ultraviolet regions. Liquid water has no rotational spectrum but does absorb in the microwave region. Ice has a spectrum similar to liquid water. Overview: the water molecule, in the gaseous state, has three types of transition that can give rise to absorption of electromagnetic radiation: rotational transitions, in which the molecule gains a quantum of rotational energy. Atmospheric water vapor at ambient temperature and pressure gives rise to absorption in the far infrared region of the spectrum, from about 200 µ1 to longer wavelengths towards the microwave region. Vibrational transitions in which a molecule gains a quantum of vibrational energy. The fundamental transitions give rise to absorption in the mid-infrared in the regions around 1650 µ1 and 3500 µ1. Electronic transitions in which a molecule is promoted to an excited electronic state. The lowest energy transition of this type is in the vacuum ultraviolet region. In reality, vibrations of molecules in the gaseous state are accompanied by rotational transitions, giving rise to a vibration-rotation spectrum. Furthermore, vibrational overtones and combination bands occur in the near-infrared region. The Hitten spectroscopy database lists more than 37,000 spectral lines for gaseous H216O, ranging from the microwave region to the visible spectrum. In liquid water the rotational transitions are effectively quenched, but absorption bands are affected by hydrogen bonding. In crystalline ice the vibrational spectrum is also affected by hydrogen bonding and there are lattice vibrations causing absorption in the far infrared. Electronic transitions of gaseous molecules will show both vibrational and rotational fine structure. Units: infrared absorption band positions may be given either in wavelength, micrometers, I1/4 m, often shortened to microns, or wave numbers per centimeter, gmA1, sometimes referred to as reciprocal centimeters. Since there are 104 micrometers in 1 centimeter, the two units are related by wave number equals 104/wavelength, wave number per centimeter is the reciprocal of the wavelength in cm. Rotational spectrum. The water molecule is an asymmetric top, that is, it has three independent moments of inertia. Consequently the rotational spectrum has no obvious structure. A large number of transitions can be observed. Lines due to atmospheric water vapor can easily be observed from about 50 I1/4 m to longer wavelengths. Measurements of microwave spectra have provided a very precise value for the OH bond length, 95.84 A plus or minus 0.05 pm, and HOH bond angle, 104.5 A plus or minus 0.3 a degree. Vibrational spectrum. The water molecule has three fundamental molecular vibrations. The OH stretching vibrations give rise to absorption bands with band origins at 3657 µ1 and 3756 µ1 in the gas phase. The asymmetric stretching vibration, of B2 symmetry in the point group C2V is a normal vibration. The HOH bending mode origin is at 1595 µ1. Both symmetric stretching and bending vibrations have A1 symmetry, but the frequency difference between them is so large that mixing is effectively zero. In the gas phase all three bands show extensive rotational fine structure. I1/2 has a series of overtones at wave number somewhat less than n I1/2, n equals 2, 3, 4, 5. Combination bands, such as I1/2 plus I1/2 are also easily observed in the near-infrared region. The presence of water vapor in the atmosphere is important for atmospheric chemistry, especially as the infrared and near-infrared spectra are easy to observe. Standard codes are assigned to absorption bands as follows: 0.718 I1/4 m, I plus or minus, 0.810 I1/4 m, I1/4, 0.935 I1/4 m, fluorine I, 1.13 I 1/4 m, I, 1.38 I 1/4 m, I, 1.88 I 1/4 m, I copyright, 2.68 I 1/4 m, X. The gaps between the bands define the infrared window in the Earth's atmosphere. The infrared spectrum of liquid water is dominated by the intense absorption due to the fundamental OH stretching vibrations. Because of the high intensity, very short path lengths, usually less than 50 I 1/4 m, are needed to record the spectra of aqueous solutions. There is no rotational fine structure, but the absorption band are broader than might be expected, because of hydrogen bonding. Peak maxima for liquid water are observed at 3450 ACMA1, 3615 ACMA1 and 1640 ACMA1. Direct measurement of the infrared spectra of aqueous solutions requires that the cuvette windows be made of substances such as calcium fluoride which are water insoluble. This difficulty can be overcome by using an attenuated total reflectance device. In the near-infrared range, liquid water has absorption bands around 1950 ANM, 1450 ANM, 1200 ANM and 970 ANM. The regions between these bands can be used in near-infrared spectroscopy to measure the spectra of aqueous solutions, with the advantage that glass is transparent in this region, so glass cuvettes can be used. The absorption intensity is weaker than for the fundamental vibrations, but this is not important as longer path length cuvettes are used. The absorption band at 698 nm is a third overtone. It tails off onto the visible region and is responsible for the intrinsic blue color of water. This can be observed with a standard UV-vis spectrophotometer, using a 10 cm path length. The color can be seen by eye by looking through a column of water about 10 meters in length. The water must be passed through an ultrafilter to eliminate color due to Rayleigh scattering, which also can make water appear blue. In both liquid water and ice, cluster vibrations occur, which involve the stretching or bending of intermolecular hydrogen bonds. Bands at wavelengths I equals 50-55 I 1/4 m have been attributed to Ts, intermolecular stretch, and 200 I 1/4 m, to Tb, intermolecular bend. The spectrum of ice is similar to that of liquid water, with peak maxima at 3400 ACMA1, 3220 A1 and 1620 A1, visible region. Attenuation coefficient for 200 ANM and 900 ANM are almost equal at 6.9 Ma1. Very weak light absorption, in the visible region, by liquid water has been measured using an integrating cavity absorption meter. The absorption was attributed to a sequence of overtone and combination bands whose intensity decreases at each step, giving rise to an absolute minimum at 418 nm, at which wavelength the attenuation coefficient is about 0.0044 Ma1, which is an attenuation length of about 227 meters. Electronic spectrum. The electronic transitions of a water molecule lie in the vacuum ultraviolet region. For water vapor, the bands have been assigned as follows. 65 nm band, many different electronic transitions, photoionization, photodissociation, discrete features between 115 and 180 nm, set of narrow bands between 115 and 125 nm Rydberg series, 1B1 are many different Rydberg states and 3A1 a 3ZA1 Rydberg state, 128 nm band, Rydberg series, 3A1 a 3ZA1 Rydberg state and 1B1 a 3ZA1 Rydberg state, 166.5 nm band, 1B1 a 4A1. At least some of these transitions result in photodissociation of water into H plus OH. Among them the best known is that at 166.5 nanometers. Microwaves and radio waves. The pure rotation spectrum of water vapor extends into the microwave region. Liquid water has a broad absorption spectrum in the microwave region, which has been explained in terms of changes in the hydrogen bond network, giving rise to a broad, featureless, microwave spectrum. The absorption is used in microwave ovens to heat food that contains water molecules. A frequency of 2.45 GHz, wavelength 122 m, is commonly used. Radio communication at GHz frequencies is very difficult in fresh waters and even more so in salt waters. Atmospheric effects. Water vapor is a greenhouse gas in the Earth's atmosphere, responsible for 70% of the known absorption of incoming sunlight, particularly in the infrared region, and about 60% of the atmospheric absorption of thermal radiation by the Earth known as the greenhouse effect. It is also an important factor in multispectral imaging and hyperspectral imaging used in remote sensing because water vapor absorbs radiation differently in different spectral bands. Its effects are also an important consideration in infrared astronomy and radio astronomy in the microwave or millimeter wave bands. The South Pole Telescope was constructed in Antarctica in part because the elevation and low temperatures there mean there is very little water vapor in the atmosphere. Similarly, carbon dioxide absorption bands occur around 1400, 1600 and 2000 nm, but its presence in the Earth's atmosphere accounts for just 26% of the greenhouse effect. Carbon dioxide gas absorbs energy in some small segments of the thermal infrared spectrum that water vapor misses. This extra absorption within the atmosphere causes the air to warm just a bit more, and the warmer the atmosphere the greater its capacity to hold more water vapor. This extra water vapor absorption further enhances the Earth unregistered trademark S greenhouse effect. As well as absorbing radiation, water vapor emits radiation in all directions. Much of this energy will be recaptured by other water molecules, but as it ascends there is less water above capable of recapturing radiation of water-specific wavelengths sent towards space. By the top of the troposphere, about 12 km above sea level, most water vapor will have already condensed to liquid or ice and released its heat of vaporization. Liquid water and ice will fall to lower heights. Temperatures at this altitude known as the tropopause are about -50 degrees Celsius. In the atmospheric window between approximately 8,000 and 14,000 nm, in the far infrared spectrum, carbon dioxide and water absorption is weak. This window allows most of the thermal radiation in this band to be radiated out to space directly from the Earth's surface. This band is also used for remote sensing of the Earth from space, for example with thermal infrared imaging. See also, hydroxyl ion absorption in optical fiber, color of water, water model, dielectric spectroscopy, references. External links, high-resolution gas phase absorption simulations, water absorption spectrum.